Good morning, everyone, and welcome. I'm delighted to have you here today. My name is Dr. S.K. Singh, and I hold a PhD in this field. Today, I will be discussing the incorporation of recovery processes in liquid dosage forms and how this impacts their shelf life. Over the course of this presentation, we'll explore the principles behind recovery processes, their application in liquid medications, and the implications for product stability and longevity. I look forward to sharing insights with you and engaging in a fruitful discussion. Let's get started. Let's start with liquid dosage forms. These include solutions, suspensions, and emulsions, which are specifically designed for rapid absorption and to ensure patient compliance. The advantage here is that they work quickly, which can be crucial for certain treatments. However, it's important to remember that these forms are highly susceptible to chemical degradation, like hydrolysis and oxidation, and also to microbial contamination. This means they require careful handling and storage to maintain their effectiveness. Next, we have recovery processes. These are procedures used to reprocess, rework, or recover materials in case of batch deviations or to improve overall yield. Recovery processes are quite common in pharmaceutical manufacturing, especially when operating under controlled GMP conditions. They help optimize resources and ensure product quality. Finally, from a regulatory perspective, guidelines such as ICH-Q1A R2 and WHO emphasize that any recovery process must not compromise the product's quality, safety, or efficacy. They also highlight the importance of maintaining the stability profile of the final product. So, while recovery processes are essential for efficiency, they must be carefully managed to ensure the product remains safe and effective for patients. Now, let's look at the impact on shelf life when we introduce additional processing steps. These steps can sometimes accelerate the degradation of the product, which means it might not stay effective or safe for as long as intended. They can also change the physicochemical properties, potentially affecting how the product behaves or its stability over time. Additionally, these processes might compromise microbial integrity, increasing the risk of contamination or spoilage. Moving on to what we call the recovery process. This is about how we address issues that arise during manufacturing or processing. Recovery processes include reprocessing, which is like correcting a batch using the same materials, or reworking, where we add a new process step to fix or improve the product. We also have solvent or API recovery, which involves reclaiming active ingredients and blend adjustments to ensure consistency. From a regulatory perspective, it's crucial that any recovery process is justified with solid scientific reasoning. And importantly, these processes should not impact the critical quality attributes, or CQAs, of the product, nor should they reduce its shelf life. Staying within these guidelines ensures we maintain product quality and compliance throughout the product's life cycle. Let's take a closer look at the critical quality attributes, or CQAs, for liquids. These are the key parameters we need to monitor to ensure product quality. First, pH is crucial because it affects solubility, stability, and bioavailability. Next, the assay, which measures the percentage of the label claim, tells us if the active ingredient is within the expected range. We also look at degradation products. These can indicate chemical breakdown over time and microbial limits, which are essential for ensuring safety and preventing contamination. Viscosity and sedimentation are important too, as they influence the product's appearance and ease of use. All these parameters directly influence the stability and shelf life of the product, so keeping them within specified limits is vital for quality assurance. Now, moving to the stability study design based on ICH guidelines. For long-term stability, we typically test at 25 degrees C with 60% relative humidity over 12 months. This simulates normal storage conditions. For accelerated stability testing, we use 40 degrees C and 75% RH for about 6 months, which helps us predict how the product might degrade faster under stress. And of course, refrigerated conditions at 5 degrees C plus or minus 3 degrees C are used for products that require cold storage to maintain stability. The shelf life we assign is ultimately based on data trends observed within these testing parameters. If the product remains within specifications during these studies, we can confidently determine an appropriate shelf life. Now let's look at the recovery process and the risk mechanisms that come with it. When we attempt to recover or restore a product, there are several potential challenges we need to keep in mind. First, recovery can introduce additional thermal stress, which means the product might be exposed to heat that wasn't present before, potentially affecting its stability. Second, there's a risk of oxidation exposure, which can lead to degradation of sensitive components. Third, microbial contamination risk increases if the process isn't properly controlled, posing safety concerns. Fourth, we may see changes in the excipient to API ratio, which can impact the formulation's overall effectiveness. All these factors can result in a higher degradation rate of the product, meaning it breaks down faster than intended. This, in turn, can lead to a reduced shelf life, making the product less stable over time. It's crucial for us to understand and manage these risks thoroughly to ensure the quality and longevity of the final product. This ties back to our overall goal of maintaining product integrity throughout its life cycle. Let's walk through this example calculation to see how the recovery process impacts shelf life. Before recovery, the rate constant, K, is 0.002 month. Using that, we calculate the time for 90% degradation, T90, by dividing 0.105 by K, which gives us approximately 52.5 months. After recovery, the rate constant increases to 0.005 month. Repeating the calculation, 0.105 divided by 0.005 results in about 21 months. So what does this tell us? The shelf life has decreased from around 52.5 months to just 21 months after recovery, which is roughly a 60% reduction. This example highlights a key concept. The recovery process, by increasing the degradation rate, significantly shortens the product's shelf life. Understanding these kinetics-based impacts helps us better predict and manage product stability throughout its life cycle. Let's talk about the microbiological impact on liquids. As you know, liquids are particularly prone to contamination, which can be a major concern during storage and use. When we talk about recovery increases, we're referring to how contamination can grow during handling steps, such as when the product is opened or transferred, and also through exposure to the environment. This makes strict control and testing essential. Regulatory requirements play a crucial role here. Preservative efficacy testing is mandatory to ensure that the preservatives in the product are effectively inhibiting microbial growth throughout its shelf life. We also need to monitor microbial limits both at the start and at the end of the product's shelf life to confirm safety and quality. The WHO emphasizes this by requiring microbial testing during stability studies, reinforcing how important microbiological control is. Now, shifting to in-use stability considerations, multi-dose liquid products require specific studies called in-use stability studies. These are because once the product is opened, exposure to the environment and handling can accelerate degradation or contamination. It's important to note that the shelf life of the unopened product isn't necessarily the same as the in-use shelf life. The regulatory perspective distinguishes between the two to ensure safety and efficacy during actual use. In summary, understanding these microbiological and in-use stability factors helps us better design and control liquid formulations, ensuring they remain safe and effective throughout their intended use. Let's take a look at this hypothetical case study involving a product many of us are familiar with, paracetamol oral suspension. This example will help us connect the dots between the concepts we've discussed and see how they apply in a real-world context. We'll explore key points like formulation, stability, and safety considerations, which are crucial for ensuring effective and patient-friendly medication. By analyzing this case, you'll see how the principles of quality control, regulatory compliance, and patient adherence come together to shape a successful product. Overall, this case underscores the importance of a thorough, science-based approach in developing and maintaining high-quality pharmaceutical products. Now, let's talk about packaging interaction. Recovery processes can potentially influence several aspects of our packaging. For instance, they may affect extractables and leachables, which are substances that could migrate from the container into the product. They can also impact container compatibility, meaning the container must not react with or alter the formulation. It's crucial that the container does not interact with the formulation or compromise its stability. Moving on to regulatory considerations. It's important to note that recovery processes are only acceptable if they meet certain conditions. First, there should be no impact on critical quality attributes, or CQAs, which are the key properties defining product quality. Second, we need to have stability data supporting the intended shelf life of the product after recovery. Third, the entire process must be validated to ensure it consistently produces a safe and effective product. If these conditions are not met, then we face some significant consequences. The shelf life may need to be reduced, or in the worst case, the batch could be rejected altogether. So, maintaining these standards is essential for ensuring product quality and regulatory compliance throughout the recovery process. Let's take a moment to summarize the key points about recovery processes in oral liquid dosage forms. These processes, which include reprocessing, reworking, and material recovery, are essential tools used under GMP conditions to manage batch deviations and to improve overall yield. Now, since oral liquids are inherently unstable systems, they are prone to issues like chemical degradation, such as hydrolysis and oxidation, and also microbial contamination. Incorporating recovery steps can be beneficial, but it's important to understand that they may also increase the degradation rate and potentially alter critical quality attributes, or CQAs, such as pH, assay, and preservative efficacy. This, in turn, could potentially reduce the shelf life of the product. From a regulatory perspective, agencies like ICH, WHO, and USB require that any recovery process is backed by solid scientific justification. Stability studies must demonstrate that these processes do not adversely impact the product, and that the product remains within specifications throughout its shelf life. In conclusion, recovery processes are acceptable only when supported by validated data that ensure the product's quality, safety, and unchanged shelf life profile. This highlights the importance of thorough validation and scientific rigor when implementing these techniques in oral liquid manufacturing. In conclusion, when we incorporate recovery processes into oral liquid dosage forms, it's crucial that we do so carefully and with solid scientific justification. Because liquid formulations are highly sensitive, any additional processing steps can have a significant impact on their chemical stability, microbial quality, and overall product integrity. Regulatory guidelines from organizations like ICH, WHO, and USB emphasize that recovery procedures should not alter the critical quality attributes of the product. Plus, the stability data we gather must support the shelf life we assign to the product, ensuring safety and efficacy over time. It's important to note that if we observe increased degradation or variability during these processes, we may need to consider reducing the shelf life, conducting further validation, or even rejecting the batch altogether. Overall, maintaining control and scientific rigor in recovery processes is essential to ensure the quality and reliability of our liquid dosage forms throughout their life cycle. For further support, please feel free to contact us. We're here to help with any questions or additional information you might need. Thank you so much for your time and attention today. We appreciate your interest and engagement throughout this presentation. If there's anything more you'd like to discuss or clarify, don't hesitate to reach out. Once again, thank you, and we look forward to staying connected.